Hello everyone, and thanks for watching Edupedia World videos. In the previous video, we saw the simplest case for solving the Schrödinger equation, the infinite square well, and in this video, we'll move on to a slightly more complicated case, the harmonic oscillator. Now, in classical mechanics, you've already done a harmonic oscillator. That is when you have a block attached to a spring and the other end of the spring is attached to a fixed wall. In that case, what you have is a force according to the Hooke's law, which says F is equal to minus kx. And obviously, using Newton's second law, this is equal to m d2x by dt square. By the way, in the previous video, we did infinite square well for one dimension, and once again, we'll do the harmonic oscillator for one dimension. That's why you only have x. And we know the solution for this in classical mechanics. The solution is x is equal to a sine omega t plus b cos omega t, where omega is the angular frequency and that is equal to root of k by m. And obviously the kinetic energy is half mv square and the potential energy is half kx square, which is equal to half m omega squared x squared. So this is the classical case. Now we'll do it for the quantum mechanical case, where instead of using F is equal to ma, we'll use the potential energy and use the time independent Schrödinger equation. So this is what will be common between the classical mechanics case and the quantum mechanics case. The potential energy will be half m omega squared x squared. Now before we go into the detail, let's see why Hooke's law and the solving of the harmonic oscillator is so important. That's because virtually any curve, if you look at it from a small enough point of view, approximated to a small enough distance, every curve can be approximated as a parabola. So let's say you have the potential energy function something like this. Something complicated, v of x versus x. Now at this point, you can use the Taylor series to, let's say this is x naught. So v at x near x naught, near these 2 points, you can use the Taylor series, and that will be v of x naught plus v dash of x naught times x minus x naught. If you don't know the Taylor series, this is a simple formula. You don't really need to know this. Plus half v double dash of x naught times x minus x naught whole squared. Plus there are other terms, but because x, this point x is very close to x naught, the other terms can be neglected, and so this is what we have. Now first of all, we can just remove v of x naught because that is the standard 0 point, and we can always shift the potential by a certain amount, and this term is equal to 0 because at this minima v dash of x naught is 0. Similarly, at this point v dash is 0, at this point v dash is 0. So v of x near x is equal to x naught can be approximated to be half v double dash of x naught times x minus x naught whole square, which is sort of the equation of a parabola. This is the same as half kx squared, except the center is not x, it is x, the center is not x is equal to 0, it is x is equal to x naught. So we see that if we look for small enough distances, we can assume that this curve is a parabola. We can assume that this curve is a parabola. If you're talking about small enough distances, we can assume that this curve is a parabola. So every curve, especially these minimas, when you look for a small enough distance near the point at which the derivative is 0, they can be approximated by parabolas or harmonic oscillators. And this is why the harmonic oscillator is so incredibly important, because virtually any graph can be approximated to be a harmonic oscillator within small enough distances. So once we solve the harmonic oscillator right now, we'll be able to use it in many different cases as an approximation. So let's look at the harmonic oscillator in the quantum mechanical case. So we have the time independent Schrödinger equation, which tells us minus h square by 2m d squared psi by dx squared. Remember, this is the time independent version, so psi only depends on x, and we have the normal derivative as opposed to the partial derivative, plus the potential energy into psi, v psi. So v is half m omega squared x squared multiplied by psi. This is equal to E psi. So this is the equation which we have to solve. And the solutions will give us solutions to a quantum mechanical particle kept in a harmonic oscillator potential. Now there are two major ways to solve this problem. One is the analytic way and the other is the algebraic way. The analytic way is quite complicated. It involves power series, but from a strategic point it is quite simple, because all you do is assume the solution to be a0 plus a1x plus a2x squared and so on, and calculate the values of the coefficients. The mathematics turns out to be quite complicated and it is quite laborious to solve it, so we will not do the power series method. We will do it using the algebraic way. But if you're interested in knowing the analytic way as well, you can read it in any book on a harmonic oscillator and you'll be able to find both the ways, and of course both ways give finally the same answer. So we will start with the algebraic way, which is simpler, which involves some tricks and some shortcuts, and it involves what we call ladder operators. And we'll see the algebraic way gives us quite a simple formulation to be able to solve the time independent Schrodinger equation for the harmonic oscillator. So let's look at the algebraic way. Now before getting into the ladder operators, we need to learn a simple concept called the canonical commutation relations, and they are known as the commutators for short. And what this is basically the difference between two operators applied in inverse orders, and for numbers this doesn't give us anything. For example, if you have two numbers a and b, this is how you represent the commutation of a and b, or the commutator of a and b. It is basically ab minus ba. Now when a and b are two numbers, then ab minus ba will be 0, are numbers or variables. But this is not necessarily true when you have operators. When you have two operators, when you apply the first and the second, it does not necessarily give you the same result as applying the second and the first. So the one we'll look at is x comma p. You can take the commutation relation of any two operators. If it is 0, we say that the operators commute, and if it is not 0, we say that the operators do not commute. And our goal is to find the commutation relation between x and p, where x is the position operator, that is simply multiplying the thing by x, and p is h by iota d by dx. This is the momentum operator. And to calculate the value of something like this, what you do is you always apply it to a function. So x times h by iota d by dx of f, a function f of x, let's say. So this will be x multiplied by h by iota d by dx of f minus h by iota d by dx of x times f. So here we apply the momentum operator and then the position operator. Here we apply the position operator and then the momentum operator. Now here, since you have the derivative of f and here you have the derivative of x times f, you can see that the difference will not necessarily be 0. And we can actually solve it to see how much it is. So this is equal to x times h by iota. By the way, this is supposed to be h bar, which is the reduced Planck's constant. Iota df by dx minus, and now we can use the product rule here. Again we get h by iota just f and then minus h by iota x times df by dx. And obviously this term cancels with this term. H by iota we can write it as minus iota h, and the minus cancels with this. So this comes out to be iota h f. So x comma p commutator on f is equal to iota h multiplied by f. What this tells us is that x comma p is equal to iota h. And this is one of the most fundamental relations which we'll use again and again. It is also the root of the uncertainty principle. We'll see that later, that whenever the commutation is 0, you have no uncertainty between the two items, but whenever the commutator is not 0, then you have an uncertainty and you cannot determine both of them simultaneously. So the commutator of x and p is iota h, and using this formula you can find out the commutator of any two operators. You can find it between x and kinetic energy, or between potential energy, kinetic energy, and so on. What you do is you apply it to an operator and then you simplify it and find out what the final result is. So for x and p, xp minus px is iota times h bar. Right. Now let's get back to our equation for the time independent Schrodinger equation. Minus h square by 2m d2 psi by dx squared plus half m omega squared x squared psi is equal to E psi. Knowing that P is equal to h by iota d by dx, we can write this equation in a better format. We can write it as 1 by 2m times P squared plus m omega x whole squared psi is equal to E psi. Right. This is the same as this if you see that P is equal to h by iota del by del x. Now what the LHS is basically the Hamiltonian operator, which is the total energy operator, because P square by 2m is the kinetic energy this, and this is the potential energy. In fact, we already saw that one way of writing the time independent Schrodinger equation was h psi is equal to E psi, where h was the operator, that's why I put a hat over it. So this is an operator operating on the function, and this is E, a number, multiplied the wave function. Now, if these were two numbers, it would be quite easy to separate them into two brackets and then solve them individually. If you have two numbers u and v, you can simply write u squared plus v squared as iota u plus v into minus iota u plus v. But we cannot do that with operators because they don't necessarily commute. However, we will look at these two terms and create operators similar to this, and we'll see that that will actually enable us to solve this equation easily. So we'll make two operators which we'll call the raising and lowering operators. A plus will be equal to 1 by root of 2h m omega. This initial term is only there to make it normalized and to make the final thing easier. The important part is what is in the bracket. Minus iota p plus m omega x. Similarly, the other is a minus, and that is equal to 1 by root 2h m omega iota p plus m omega x. Right. So when we have this, we try to calculate the value of a plus into a minus. And let's see what that is. We'll actually need a minus a plus, so we'll do that. That is equal to 1 by 2h m omega times the product of these two terms. So that will give us p squared plus m omega x whole squared, and that will give us another term minus iota m omega times the commutator of p and x, xp minus px. Right, you can try to solve it at home, and when you multiply these two, this will come. Minus iota p into iota p is p squared. This multiplied by this is m omega x squared. And then you have minus iota m omega. The first would be x times p. The second would be p times x. Right. But we already know what the commutator of x and p is. That is equal to iota h. So what we get is a minus a plus is equal to, and here divided by h omega, everything else is the Hamiltonian. So what we get is Hamiltonian by h omega plus, and then m omega cancel. This is equal to iota h. Iota h multiplied by minus iota is 1. The h cancels. So plus 1 by 2. And this is the relation, a simple relation. A minus a plus is equal to the Hamiltonian by h omega plus half. This will enable us to solve this equation quite easily. So let's see what we have till now. Let me write it in a little bit better form. What we have is two operators, a plus and a minus. I'll just write them in the same formula, which is 1 by root of 2h m omega minus plus iota p plus m omega x. Remember that a plus has minus iota p and a minus has iota p. From this, we were able to calculate a minus a plus, and it comes out to be the Hamiltonian by h omega plus 1 by 2. From that, we can write the Hamiltonian as h omega times a minus a plus minus 1 by 2. Now you can do a plus a minus for yourself, and you'll see that it comes out to be h by h omega minus 1 by 2, which means that the Hamiltonian can again be written as h omega times a plus a minus plus 1 by 2. Another thing this tells us is that when you take the commutator of a minus and a plus, that is a minus a plus subtracted by a plus a minus, so these two will cancel, we'll get 1. So a minus and a plus are what we call the raising and lowering operators, have this nice relation that their commutator is equal to 1. Now you might be wondering why we've done all of this, and the reason is a minus and a plus have a very simple result, which I'll prove in a minute, but I'll just write it down right now, and it's important, so I need you to understand this one. It says that if psi satisfies the time-independent Schrodinger equation with energy E, then, and we'll prove this in a minute, a plus psi satisfies the time-independent Schrodinger equation with energy E plus h omega, and also a minus psi satisfies the time-independent Schrodinger equation with energy E minus h omega. So I'll prove this in a minute, but first let's understand what this tells us. If we have a function psi of x, somehow we are able to get one function psi of x which satisfies the time-independent Schrodinger equation with the energy E. That means we have a solution of the equation h psi is equal to E psi with an energy E for a particular psi. Then once you apply a plus to that psi, a plus is this operator, then you will get a new wave function a plus psi, and that will satisfy the same equation with a different energy E plus h omega. So this is why a plus is called the raising operator. So this doesn't enable us to calculate a solution directly. What this enables us to do is, if we have one solution, we'll be able to get many other solutions. So by some method you may have found one solution psi which satisfies the equation with energy E. You just apply the raising operator once and you'll get a new solution which satisfies it with energy E plus h omega. You apply the raising operator again, you get another solution with the energy E plus 2h omega. Similarly, a minus is the lowering operator. If you have a function psi which satisfies the equation with energy E, then a minus psi, which is a new function, will satisfy the same equation with energy E minus h omega. And so you have these two operators, raising and lowering, which tell you that once you have a single solution and the energy of that solution, you can get an infinite number of solutions with basically different energies simply by applying the raising and lowering operator again and again. So I'll prove this, and then our goal will be to find one simple solution, and after we found one solution, we'll be able to apply the raising and lowering operators and get all the other solutions. So before that, let's prove it. I'll prove the first one, and the proof for the second one is similar, and you can do that on your own. So we know that h psi is equal to E psi for some particular value of psi of x. What we want to calculate is h of a plus times psi. And what is that equal to? We can write h as h omega a plus a minus plus half, this is what we saw a few minutes ago, times a plus psi. So this is what we need to simplify, and this we can write it as h omega times a plus a minus a plus a plus by 2 times psi. And now that we can write as h omega a plus. Now we take the first a plus common. What we have is a minus a plus plus 1 by 2 times psi. And now we can use the commutation relation a minus a plus is equal to 1 to write a minus a plus in terms of a plus a minus. So this is equal to h omega a plus times a plus a minus and then plus 1 plus half. So plus 3 by 2 times psi. Now we'll use the same thing we used here, that the Hamiltonian is h omega times a plus a minus plus half. So what we get is h, which is a plus a minus plus half, and then we have plus 1, so another plus h omega, and a plus times this whole thing psi. And what we know is h psi is equal to e psi, so this tells us this is equal to a plus times e plus h omega times psi. And now e is not an operator anymore, it is just a number, so we can write it as e plus h omega times a plus psi. And the result finally we get is the Hamiltonian of a plus psi is equal to e plus h omega times a plus psi. So notice this, we knew h psi is equal to e psi. That means psi satisfied the Schrodinger equation with energy E. And then we are able to calculate this, that h of a plus psi is equal to e plus h omega times a plus psi. This is basically equal to h psi dash is equal to e dash psi dash, where psi dash is a plus psi and e dash is e plus h omega. So we've proved this result, that once you have a function which satisfies the equation with energy E, you just apply the raising operator once, you'll get a new function, and you don't need to see that verify it, you've already proven that that will satisfy the equation with energy E plus h omega. You can do a similar result yourself and prove that h times a minus psi, assuming that this equation is true, of course, h times a minus psi is equal to e minus h omega times a minus psi. So now we finally see the benefit of using these raising and lowering operators. All you need to know is one solution and its energy, and you've been able to calculate every single solution using the raising and lowering operators. So now all that's left is to try and find out one single solution for this equation, and by applying the raising and lowering operators, we'll be able to figure out all solutions. So let's say we have one solution psi at an energy E, and we apply the lowering operator. We get a solution a minus psi with energy e minus h omega, and we keep applying it. Eventually we'll reach a point where we'll find the lowest state psi naught, which will have the lowest energy e naught, and then when we apply a minus psi naught, we should get 0, because the lowest energy would be e naught, and anything lower than that would give us a total energy of 0, because it would not be possible. So this would be the lowest energy, or the ground state. And how do we find the value of the ground state? We use this equation, a minus psi equals 0. So what we have is 1 by root of 2h m omega, and then we have iota p, so we'll have h d by dx plus m omega x times psi naught of x is equal to 0. And using this, we have to find out the value of psi naught. So this is quite simple. You can just standard kind of calculus, and what you'll get is d psi naught by dx is equal to minus m omega by h. This can obviously just be cancelled out because we have equal to 0. D psi by dx is equal to minus m omega by h x times psi naught, and we can just integrate it. D psi naught by psi naught is equal to minus m omega x by h dx, which basically gives me ln of psi naught is equal to minus m omega x squared by 2h plus a constant c. And basically this gives me psi naught is equal to A times e to the power minus m omega x squared by 2h. So it is exponential and Gaussian in that it is a e to the power minus m omega square x squared by 2h. E to the power minus kx squared is a Gaussian curve, as you know, and we can also directly find out the value of a using normalization. So 1 is equal to integral of psi star psi, so that will be a squared e to the power minus m omega x squared by h, because we multiplied the two, dx, and this should be equal to 1. But we know what the value of integral e to the power minus m omega square x square by h will be. So that will be a square times root of pi h by m omega. If you don't know this is a standard Gaussian integral. You learn it in your mathematics class soon. And what that tells me is a is equal to fourth root of m omega by pi h, 1 by 4. So finally what we get is, I'll write the solution here. The ground state, which means the state which has the smallest energy, has psi equal to m omega by pi h to the power 1 by 4 times e to the power minus m omega x squared by 2h psi naught. So this is the ground state, and using the raising operators we can find psi for any other value. Let's try to find the energy of the ground state as well. We know that h psi naught is equal to E naught psi naught, and we know that h can be written as h omega times a plus a minus plus 1 by 2. So this into psi naught is equal to E naught psi naught, but we already know a minus into psi naught is 0, so we simply get the energy to be h omega by 2. So E naught is equal to h omega by 2. So let me write this down properly. The psi naught x, which is the ground state, has the function m omega by pi h to the power 1 by 4. This is only done as a normalization constant to make the probability 1 into e to the power minus m omega x squared by 2h. And the energy E naught for the ground state was h omega by 2. So what will be psi 1 of x? That will simply be a plus times psi naught of x. You can calculate it yourself. And the energy E1 will be h omega by 2 plus h omega, so 3h omega by 2, and so on. The nth state wave function psi n of x will simply be an is just the normalization constant, times a plus to the power n. You have to apply the a plus operator n times psi naught of x, and the energy En will be n plus half h omega. So that does it. We've been able to finally solve the Schrodinger equation for the harmonic oscillator. We have a ground state which is equal to m omega by pi h to the power 1 by 4 e to the power minus m omega x squared by 2h. And then obviously we can find excited states by applying the raising operator a certain number of times. This is just the normalization constant. And we can also find the energies, which is n plus half h omega. So this completes the harmonic oscillator. In the next video, we'll study what essentially should have been our first case, except it's not very simple, and that is the free particle under no potential or forces whatsoever. A free particle moving without any forces, and we'll see what that looks like from a quantum mechanical perspective. Thank you.